Next, we go to explaining pen and paper puzzles with the MUSes. I think we are presented by Christopher Jefferson. Christopher, please share your screen and yeah, please introduce yourself and floor is yours.
Thank you. Hopefully everything will be functioning correctly. I've been having some internet problems recently, so if you stop listening, if you stop hearing me, please give me a poke. Anyway, so I'm going to talk about solving pen and paper puzzles with MUSes, and I will explain what these words mean. And this is joint work with a whole bunch of people at St Andrews. I don't list all of them, but they're very good. So just to give you a kind of overview, so I will explain what a pen and paper puzzle is, but intuitively a pen and paper puzzle is a puzzle designed to be solved with pen and paper. So the classic example is Sudoku. Kind of think anything you would see in the puzzle section of a newspaper. I will say we are not going to do crossword puzzles. So we're not interested in like we're not interested in like language interpretation and things. So, but Sudoku, and there's loads of these puzzles, Binaru, Kukuru. The reason people talk about pen specifically is it's usually assumed that users will not solve these with a, like you don't use pencil and erase it when you make a mistake. The intent, people talk about solving them with a pen to mean you fill in a value when you know it, and you should never go back, you should never make a mistake. And what we have created is a system which works on any such puzzle in principle. The puzzles are written in a high-level constraint language. For those who know about constraint programming, we use an existing constraint language called Essence. And the plan is we have an AI system which solves these puzzles in a human-like manner for some definition of human-like. One thing which makes this area kind of both easier and harder is we kind of know these puzzles are designed to be solved by people. And just to say, like, so if you've never seen it, this is a YouTube video. It got like nearly 3 million views. It might have 3 million by now. This is a YouTube channel where they solve puzzles like this. So this is in this community, a famous example called the Miracle Sudoku. It's like Sudoku with some extra rules. If you've never watched this video, I would recommend it. It's very entertaining. And the person literally explains how to solve the puzzle. This is the entire video. You can see it takes 25 minutes. It's not quick. So the question is, can we make a system which can produce explanations similar to and maybe even higher quality than a human? So to start with, we're going to assume that we write these puzzles in this high-level language Essence, which already exists. Now, and this is kind of related to what Kieran was just saying in the previous talk, existing AI systems, so SAT solvers, we work on a solver called Minion at St Andrews, interlinear programming. Broadly speaking, if a puzzle is solvable by a human, these systems solve it in milliseconds, like a small number of milliseconds, 3 or 4. There's the odd exception, but generally speaking, if a person can solve it, it's trivial for a computer. Now, popular puzzles do have special solvers. So people have written solvers. So if you've never come across this, there are literally hundreds of books on how to solve Sudoku. And they tell you techniques for solving Sudoku with names like X-Wing and Jellyfish and Death Blossom. And so people have written solvers where they take those rules and implement them, but they're usually problem specific. So I could try to solve it with Minion and then explain to a person how Minion solved it. This is, as I said, just by coincidence, this is a bit like what Kieran was talking about. So how would Minion solve a puzzle? So this is a puzzle called Star Battle. So the rules are, we're going to put stars on this grid. There must be a star in every row, a star in every column, a star in every cage, which are the kind of dark outlined boxes, and stars cannot be adjacent horizontally, vertically, or diagonally. And so what Minion would do is it would look at this, it wouldn't do anything, and it would say, right, I'm going to guess the top left is not a star. And it would then deduce just below that there has to be a star, because there's only one place left in that box to have a star. And then it would go, I'm going to guess this isn't a star, and this, and this, and this, and this. And now I've guessed this isn't a star. Well, this thing at the end has to be a star. then, and I've kind of merged together a bit now, but basically the only place left for a star in the third row at this point is that star I filled in. And if you carry on deducing a little bit, you'll figure out that there can't be a star in the top left, top right, using fairly simple steps. So it's like, right, that's not a star. So let's try putting a star here. And once again, if you run through, you'll very quickly figure out you can't put a star there. And no. So eventually we're like, oh, well, there must be a star in the top left because everywhere else in the top row wasn't allowed to be a star. And then we start going along the second row going, no. Let's try putting a star here. So now we can figure out, now we'll guess there isn't a star here. That fails, so we do put a star there and you carry on down. And this is literally what Minion does. We can print out its search tree and what I just described is what it does. This seems to violate many of the rules. What I did, if I did all of it, I could explain it to a person. They would be able to understand what I was doing, but I have violated the rule of pen and paper puzzle. Like I clearly filled in stuff, it was wrong, I went back. So this isn't how people solve them, and this is not, people don't enjoy this type of explanation in our experience. So how do people solve this? So if we look at the first row, there's a little cage at the top. So one of those top two things has to be a star, because there has to be a star in every cage. So the star in that first, column, the star in that first column must be in the top two cells. So there isn't a star anywhere else. And similarly, along the bottom, there's a little 2-element cage. So there's no star anywhere else in that bottom row. And after we've done that, there's only one place left in that bottom right-hand cage for a star to go. So a star has to go here. So now we can also deduce that there's no star, like that top box that kind of looks, I should have got like for some reason my computer's not letting me highlight and I realize you can't see where I'm pointing. So that top box has to have a star in it, one of those 5 things in the second column, so there can't be a star at the bottom. So now there's only one place left for the star to go at the bottom, so we put the star in and we carry on. Going back to that very first thing we did, because it's the easiest one to understand. So why did Minion not fill in those blank squares in that first column? Sorry. The reason is that it looks at constraints in isolation, because that is, it turns out, the fastest way of solving problems is you look at every constraint in isolation, and then when you've finished, you just branch. And it turns out, experience tells us that's the fastest way of writing a solver. In this case, we've used 2 constraints simultaneously. We've used that there is a star in the first column, and there is a star in the top 2 boxes together. So our sort of working hypothesis, and by the way, I don't claim we have solved the problem, we're just working towards it. Computers make all possible deductions that involve one constraint. This is what constraint solvers normally do. And then they basically branch a lot and do a lot of search, and maybe they do some learning. Human players don't branch. What they do is they look at a little bit of the problem, and this is where I am simplifying. Think very hard about that little bit of the problem until they can figure out where there is or isn't a star. And then they fill that value in, and then they see if they can make further deductions in the rest of the puzzle. And we do provide evidence for this in our paper. We can look at tutorials for how puzzles are supposed to be solved for a large range of puzzles. And those tutorials will often say things like, there isn't a star in this row or this row and this column, and therefore this. Like, they often don't explain the intermediate steps. They're just like, think about these 3 things and you'll realize that something has to go here. Not always, but it is a common occurrence. So to do this computationally, we want to prove that given some cell and some value for that cell, so in the case of star battle, it's star or not star, in all solutions, there is a star here or there isn't a star here. Usually puzzles only have one solution. That's a general rule, but it's not a requirement for our system. So what we want to find is the smallest subset of the problem where you can still correctly deduce that variable has to take that value. And if you get too small a subset, there'll be solutions to that bit where it doesn't take that value. Implementation details, instead of finding instead of trying to find subsets where in all solutions C equals V, we look for subsets where in all solutions, there are no solutions where C is not equal to V. And the reason for this is the study of finding the smallest bit of a problem which has no solutions is an existing research area called minimum satisfiable set. This is where the MUS comes from. And there's been loads of research on these. They come up in explanations all the time. And the idea is if you have a big unsolvable problem, you're trying to find the smallest bit that isn't solvable. And that can be useful to explain to people, like, why can I not make my schedule? Oh, well, it's because this little bit of the schedule was unsolvable. But here we're using it in sort of reverse. We're saying, in this problem, there is a star here. And the reason there is a star here is in all solutions, there can't not be a, like if I make it not a star, there's no solution. So there must be a star here. And then I use that as a series of steps to fill the whole puzzle in. So an unsatisfiable set is any subset. A minimal unsatisfiable set is a set where you can't take anything else out. There will often be many unsatisfiable sets for each thing you can fill in. There are many algorithms for finding MUSes. We did find the majority of them were too slow for our purposes. And we think the reason for this is that they tend to be designed to solve very large, very hard problems where the MUSes are often hundreds of constraints big. Once again, people couldn't interpret something that big. In almost all cases, our MUSes are smaller than size 10, and they're often size 2, as we saw in the previous problem. So we have little MUSes. So we need to do a lot of problems, because for every value in the grid, we need to find the smallest MUS to find the next step we should do. And then if we filled it in, we have to find all the MUSes again. You can keep some caching between steps, but it's not super easy. So we've got special algorithms which are designed for finding very small MUSes. And these algorithms, once again, I'm just going to mention back to Kieran, we do very badly on existing benchmarks, which are designed for incredibly hard problems with massive MUSes, but they do very badly on our problems, which are really small, comparatively small problems with tiny MUSes. So swings and roundabouts. So this is just like the basic overall idea is we take our puzzle in our high-level language. Our high-level solver, our high-level language essence, there's a solver called Conjure and another one called Savile, and they will convert it into CNF, suitable for giving to a SAT solver. So this is what we would do if we were normally going to solve the problem. One of the things, we turn it into a SAT problem, give it to a SAT solver, finished. We still turn it into SAT, but rather than just giving it to a SAT solver, we have a list of the variables which are the choices the player has to make. So they'll be the values for, like, if this is true, there's a star. If this is not true, there's not a star. And also we add a list of variables that can be used to turn the constraints on and off. So there'll be one that says, like, if this is true, the first row has a star in it. If this is false, it doesn't mean there isn't a star, it just means nothing. And then these MUSes are, you turn on as few of the constraints as possible and still have the problem have no solutions. For all the locations in the grid, we go and we see what the smallest explanation is. And we keep going till we solve it. I'll just mention that this is similar to work by Bogarts, I'm probably mispronouncing that and I do apologize, who did a paper in ECI 2020. So they were looking at a particular type of puzzle called logic puzzles, and we were simultaneously looking at some other puzzles. But it's this idea, we are not unique in coming up with this idea. They published it first. So I'll just attempt to, I think I have enough time, so I will give you a brief demo. Has a window just appeared on top of the presentation? So this is the example I went to in the talk. So this is our system running on that puzzle. And so it says, and I apologize, the colors maybe don't come through very well. It says there is at least one star in that top left box, and there is at most one star in the first column. So we split up, there is one star into at least and at most. So we do some work on trying to produce nicer explanations. And it says because there is one star in that box and at most one star in this column, then all of these things are 0. So there are no stars down here. So notice we are not yet, and this is an important next step, we're not explaining why it's true. We're just telling you what you have to think about. And then it similarly along the bottom says, similarly, there's at least one star in the box, and at most 1 star in the bottom row. So we can zero out all the things along the bottom. Then it makes what it calls a simple deduction. So a simple deduction is something which only involves one of the constraints. So in this case, it's saying there has to be a star in that bottom box 7. So I'm going to make this 1 because there has to be a star somewhere in that box and there's only 1 place left. Then because there's a star there, there can't be another star in the same row or same column or next to it diagonally. So all of those get knocked out. Then we get another interesting deduction. So now there's only 2 things left in this box. So the other things in this column can't be a star, so it knocks those out. And it carries on, and similarly, it says, similarly in this column, there's only 2 things left in this box, so these can't be. And then I can just, I won't go all the way through because I'm running out of time, but I can continue through, and eventually it gets to the point where it makes it. But the important thing about this is none of this is tailored to star battle. There is a high level, just logical explanation of it. And I could, I'll just very quickly, just as a proof of principle. So we have a list of examples here. So if I go to, there is another puzzle called Tents and Trees you might have heard of. I'm not going to explain this puzzle, but I'm just going to point out that in the same way I can say solve Tents and Trees, and it produces similar explanations. Thank you very much. I'm open to questions.
Thank you, Chris. That was really interesting. Thank you for the demo. I'm sure everyone enjoyed that. If you have any questions, please raise your hand. Yeah, so Kyle has a question. Please go ahead.
Yeah, that not being able to raise your hand as the host thing's really coming back to bite me. No, thank you very much for that presentation, Chris. One of the things I was really interested in was that the explanation you're tailoring here kind of has an interesting balance in that we're trying to approach the actual decision making in a way that is more interpretable to humans. So we're bringing in that human element to the actual problem solving, even though we know we've got all these wonderful ways that we could search and solve the problem through an endless string of deductions, as you say, but by bringing in that human element, we're able to explore it in a way that's naturally more interpretable to humans. I think one of the, I think that's really interesting. However, it must presumably bring up, from the other perspective, it creates more work on the computational side. So I'm wondering what you're thinking about the balance between using learnings from users and what users find useful in their explanations to inform decision making versus what the trade-off might be for, I don't know if this solver was going to pass on to another computational process or something like that.
So I will say, so actually this is, so definitely our intention here is producing explanations for people. So this is definitely and like, I mean, Kieran was saying his proof logging is like 1,000 times slower. We beat that by a lot. I think the Miracle Sudoku minion normally takes, I think like 14 milliseconds. And producing a full explanation of the Miracle Sudoku takes our system on a 32-core computer about 6 hours. So I mean, we can almost certainly do better than that, but it is incredibly slow. This is definitely not, yes, as you said, this is definitely not a useful way to solve problems. And one thing we do is the first thing we do when someone gives us a puzzle is first we just go solve it normally just to check they haven't given us an unsolvable puzzle. So actually, in some sense, the computer knows it's solvable in the first kind of half dozen milliseconds of solving, and then the next 6 hours is explaining it to the player. I should have mentioned this more thoroughly. So I've just got up a list of the things we do. So I should have, sorry, I'm going to sneak this into the question. All of these puzzles, we went through online tutorials and showed we matched the same reasoning as the online tutorials. So one thing we really wanted to do was try to get as close to existing human reasoning as possible, kind of regardless of how long it took. And there is, as I said, we don't always match perfectly. And also important clarification, well, not clarification, I said this in the talk. In some cases, it can be non-obvious why a certain subset of the constraints makes a certain deduction. And in some cases, the online tutorials do tell you why. They give you an English description. And we don't yet try to do that. That's what we'd like to do next. And we don't know how to do that yet. In a way, because it's often kind of just free text. Sorry, that was not a direct answer. But yeah. So this is definitely a terrible way of solving problems, but hopefully a good way of explaining why. And also there's other kind of applications like you can hopefully use this to do things like measure difficulty of problems because you know how a person solves them.
That was going to be my exact follow-up question is about cognitive load and stuff like that. This might be a good indicator for something like that, where from a computer we have a kind of skewed version of what the complexity of a problem might be, whereas this would give you a sort of complexity that very closely mirrored the human viewpoint.
So
yeah, so Chris, Pam, and Kyle, I'm sorry I had to stop here for this, but it's making interesting conversation. So I hope you all take it to the breakout sessions in the future. So we'll move on to the next presentation. Thank you, Chris. Next, we have Sandy Brownlee presenting mining Markov network surrogates to explain results of heuristic optimizations. Sandy, if you can, please share your screen.
Okay, hopefully you can see that.
Yes, that sounds good. Yeah.
Good stuff. I'm trying to go for the prize for the longest title. Okay, so yeah, this talks a little bit, well, it's on the same kind of territory as the last couple, in that it's about optimization problems, but it's using meta-heuristics or randomized methods rather than the terribly clever integer programming and exact methods. And it's basically some work I've been involved with for a number of years, and I'm starting to look at it in a bit more depth again with my PhD student Aidan and his co-supervisor David. So, quick overview of what I'm planning to say. I'll talk a little bit about my view on explainability and optimization. It's a little bit different because it's a bit more focused on visualizations. And then I'll talk about mining a Markov network fitness model, which is the specific approach that I've been using, before giving a couple of examples, one with a toy benchmark and the other one with a more concrete problem in building optimization. So to begin with, the approaches that I'm looking at are meta-heuristics. That's a whole family of things that includes genetic algorithms, particle swarm optimization, hill climbers, simulated annealing, all that kind of stuff. And in all of these approaches, you've got a meta-heuristic, the algorithm, which is generating solutions. So we've got the meta-heuristic is just kind of over here. I'm not sure if you can actually see my pointer. If someone can nod at me, that would be helpful.
We can see the pointer, yeah.
Oh, excellent, tremendous.
Yeah.
Right, so there's a little red dot here. So the meta-heuristic, by whatever means, is generating solutions, and they will be designed timetables, schedules, allocations of jobs, whatever it might be, and they're being measured against some kind of fitness measure. So that is counting how many constraints have been satisfied, running a simulation of performance or some cost modeling or something else. But whatever it is, it's giving us a quality measure of our solutions. It's giving us a number, which we tend to call fitness. That gets fed back to the meta-heuristic. Meta-heuristic makes decisions on that basis and produces some new solutions that are hopefully good. And out pop at the end some optimal, or at least near optimal solutions. And that's great, and it works pretty well for a lot of problems. The problem is that it's treating the optimization problem as a black box. In fact, to most end users, the solutions are coming out at the end without really any justification or anything. So they're needing to be taken on trust. And I think as the general feeling among the workshop goes, that's not really good enough. in particular for optimization problems, the kind of real world problems that I've worked with in the past, we might want to know a couple of things. One of them is whether we've actually managed to solve the problem, or if we've just found an error or a loophole. I think that was kind of touched on in the last talk, or it might have been the one before, but has the optimization algorithm, which is very good at finding the best solution in the context of the problem that it's been given, has it just found a loophole, or has it actually solved the problem that the person wants to solve? And in light of that as well, we might want to know what characteristics are actually crucial to making a solution optimal, and which ones are just artifacts of this random process that's going on. And we'll see an example of that when I come on to my real world example. Are there things that we can change about the solutions that will make them a bit more appealing, or a bit more preferable in some way, without affecting their optimality? And I propose that we can address both of these things by highlighting the sensitivities and the linkage in the problem variables. And this talk is about one approach to doing that, using what are known as surrogate fitness models. So a little bit of context before I go into the real meat of the talk. What are surrogate models? Well, the little diagram I had up before, we can extend that with this thing over on the right, the surrogate. Basically, the idea is that meta-heuristic is calling this fitness measure a lot. And if that's a very long-running thing, like a simulation of some kind, then that means that the meta-heuristic will take a jolly long time to solve the problem. So the meta-heuristics community have introduced these things called surrogates. It's basically use a machine learning approach to train a fast-running model on what solutions look like. So you present that model with some solutions and their fitnesses, and that model learns what a good solution looks like and is then able to make predictions. So we call that surrogate in place the real fitness measure some of the time in order to predict the fitness of some of the solutions. And the whole purpose of that is that we don't have to call the real fitness measure an awful lot, and so we can speed up the search. But I think we're kind of missing a trick in our community here, because that surrogate model is also an explicit model of the problem. It's another capturing of what the algorithm understands good solutions to look like. So we can exploit that to produce something like an explanation for what the algorithm has done. So I'm going to introduce now a specific kind of surrogate model known as the Markov network fitness model. It's designed for bit string encoded problems, and it was originally developed as part of what's known as an estimation of distribution algorithm, an EDA called DAEM, and it's an undirected probabilistic graphical model. Basically what it boils down to is a linear sum of functions over the variables, relating them to the negative log of fitness, and we can use that as a surrogate model. A little bit of an example to show how it works. So let's say we've got a very simple 4-bit problem, which I've illustrated on the right. The nodes there are the variables, and then edges between them are some kind of dependencies, connections between them. So if it was a timetabling problem, they might be people who can't be in the same room at the same time, but it might be any number of things. So we've got some connections between the variables, and we've potentially got higher order connections. So you could say that x0, 1 and 3 have got a 3-way connection. And the model just looks like this. We've got a series of weighted terms, and you can see there that there's a term for each of the variables on their own. There's ones for pairwise interactions, and there are a couple of terms for the 3-way interactions plus a constant, and that's all related to the negative log of fitness of a solution f of x. And we use a population with the fitness of that population to train that. So a population is just a collection of solutions that we've evaluated. So it might look something like this. Here we've got a population on the left, some binary encoded solutions with their fitnesses. We'd substitute them into that function that we had on the previous page, and you'll need to take it on trust. It looks like this. And we can then solve that using a least squares fit to give us our alpha values. So those alpha values specify our model, and we can go in the opposite direction to that in order to predict fitnesses. So for a given individual or a solution like this one here, 1011, we can substitute back in to our equation there. We know what those alpha values are. We worked them out using the population before, and we can get the predicted fitness from the model as f of x equals e to the negative u of x. So basically e to the power of the negative of that function there. So I can go into a lot more depth on that, but I really don't think there's an awful lot of time to do that. You can take it on trust here that there is a linear model sitting behind this and that we can use it to predict fitness. And because it's a linear model, it's also, at least to an approximation, interpretable. Right, we can take those alpha values and use them in some way. Oh no, I forgot I put this slide in. Yes, we can use it as a surrogate. We can speed up optimization. You can go and read those papers if you're really interested in how to do that. But yes, as I propose, this is also the basic building block of an explanation. So how does that work? Well, that model there was trying to predict fitness, and it was more accurately trying to predict what makes fitness high. And so if we remember, there's a negative log relationship to fitness there. So if we're interested in high fitness solutions, and the high fitness solutions are likely to have a 1 for a particular variable, then the corresponding alpha that goes with that term in the model is negative. And likewise, if the variable should be a 0, which for mathematical reasons gets encoded as a -1, then the alpha that goes with that should be a positive. Key message here: if the alphas are negative, we want there to be 1s for those variables. If they're positive, then we want there to be 0s for those variables. And if we don't care in the optimal solutions what value they take, then the alpha will be around about 0. Likewise, if we've got pairwise terms, if the variables should be the same as each other, then we would expect the alpha to be positive. It will be negative. There's an awful lot of positives and negatives in this one. And if they are opposite to each other, then we'd expect them to be positive. And it's all because of this negative log relationship with fitness. And higher order interactions kind of go on. With each level of interaction, we can look at the sign of the alpha value in the parameter in the model, and that'll tell us what we think good solutions should look like. Much easier to see it in the way of a couple of examples. So here is a toy problem, and this is properly a toy problem. It's known as the checkerboard function, and it's really designed for testing meta-heuristics. The idea is that we've got a binary encoded solution, and we arrange the variables into this grid pattern, and the fitness function there is just to count the number of neighbouring pairs of variables or squares on the grid that are opposite in value. So the optima for this problem are 2 grid patterns, and if you coloured them as black and white rather than 1s and 0s, they would look like this. Now, if we construct a Markov network fitness model over a population of these solutions, and genuinely for a grid like this, which is 64 squares, you'd need around 100 solutions, just a few more solutions than there are unknowns in the model. You can get reasonably good indication of what the good solutions should look like just from that, rather than running the meta-heuristic. So we get things like this. So here are 2 sets of alpha values coming out of the model. The ones on the left, what we call the univariate terms, the ones for each separate variable. And you can see there that over a few models, they've all floated around 0. And that basically means we don't care whether they are 1 or 0. We don't care if they're black or white. And that's true. The 2 optima have equally 1s and 0s in every position. But the ones over on the right, these are the bivariate terms for the neighbouring cells in the grid, and you can see they're all positive, and that's basically saying we want neighbouring cells to be different to each other. So the model has picked up this characteristic of what makes good solutions good. You'll also see that some of them are about twice as high as others, so they've got twice the importance. You might be able to guess which ones these are. Turns out they're the ones in the middle of the grid. Okay, so they're the ones that I've coloured in red here. So again, the model has kind of picked up something quite subtle about what's going on with the fitness function. Something that might be interpreted as being an understanding of the solutions that the algorithm has seen over its course as it's run. So now I move on to what I jokingly call my more concrete problem, mainly because it's buildings related. Here we've got an optimization problem where there isn't a trivial mathematical function to evaluate fitness. Here we've got a long-running building performance simulation. The goal here is to find where to glaze this wall. So this here is a building over on the right, and we've got a grid of 120 cells, and we're wanting to either put glass in them or not. So either just leave them as concrete or make them glass. And it's actually a multi-objective problem. So we're the work that I've done on this problem in the past is that we're trying to minimize the energy consumption for lighting, heating and cooling, and we're trying to minimize the cost of building the wall. If there are more windows, it's more expensive to build. If we make the thing completely glass, it's a greenhouse, so you've got to run the air conditioning all the time. If you make it no glass, then you need to run the lights all the time. And if you're somewhere in between, then there might be a bit of a sweet spot. So it's not a particularly easy problem to solve, partly because you've got this long-running building performance simulation in the background, which takes off the order of a few minutes for a single evaluation. So by the time you're looking at thousands of them for a meta-heuristic to solve the problem, it will be taking a long time to solve. And this is originally the motivation for running a surrogate fitness model as part of the optimization. A little word on the optimization results. We used a very well-known and rather old now multi-objective genetic algorithm called NSGA2 to find an approximated Pareto front of solutions to this problem, and it looked like this. So basically each of the zigzagged lines in this front here corresponds to a particular solution. I've highlighted 3 of them there. So there's a low-cost one, which is probably quite horrible to be in that building because it's almost all concrete, and then at the high energy efficiency, so minimal energy, maximal cost, and we've got lots of glass, and then there's something in between. And already there's a few things that stand out there, right? There's a random process going on. It's missed the minimal cost of no windows, and there's a really weird shape to this window. Is that actually something that we can do anything about? Well, that trade-off already are quite helpful. Anyone who's done work with multi-objective or multi-criteria decision-making knows that is a very informative process, and it's helpful to know what that trade-off is. But we might want to know what other things we can do with those solutions. Can we tweak them? So we tried fitting, we tried a number of things. We tried basically perturbing the solutions and running the simulation lots, and that's fine, but it basically involves a lot more extra CPU time. So we thought, well, let's try mining the surrogate model and see what comes out of that. So to begin with, we tried a Markov network fitness model with both terms for the neighbouring cells on the grid, but also terms for each separate variable, and it was trained on the 400 highest fitness solutions from the first part of the run. And what we got out for the coefficients for energy, so there are 2 separate models here, I should say. There's one for energy and one for cost. For energy, it looked like this, so what appears to be a lot of positive values and then a lot of zero-ish values. And cost, well, much the same kind of picture. And it turns out that these values floating around 0 are the ones for the interactions between the cells. So we found that there don't seem to be any interactions between the cells. So we tried rerunning things using a much simpler model, just looking at the univariate terms, the ones for each variable separately. And we get a slightly nicer picture coming out. So again, we got these positive terms, and you can see that there's a bit of a bias. They're kind of increasing as we go over to the right there, and if we put them onto a heat map as we have over on the left here, we get some kind of an idea here that we've found that cells in the middle and kind of the upper region, they're the ones that should be getting glazed, and the ones elsewhere should not be getting glazed. So we've got an idea now of which cells are more important, which ones we want to have glazing in the optimization of energy. If we do the same thing for cost, all of the values are basically about the same, basically saying that the contribution of each cell to cost is equal, and that makes sense because the cost model we used was just to multiply the number of windows by a fixed amount. So we've got 2 very clear ideas there about the relationship between our variables and the problem and what makes a good solution. I promise we're nearly done, maybe another minute or so. So the nice thing about this is what we've got coming out is information that we got from the optimization run without running any extra fitness evaluations. In fact, actually there was a time saving because we're using a surrogate to speed things up. And we've rooted this analysis in multiple generations of the run. So it's been kind of biased towards what the algorithm has seen of the problem. How we feed this back to the decision maker? Well, as you could see, it was through visualizations, knowing the sensitive variables, we can safely start to adjust some of the solutions for things that we haven't included as part of the optimization. So fixing the odd window shapes, knowing that actually more glazing in this area is probably helpful and adding it elsewhere is less helpful. And it gives us some kind of a confirmation. If the solutions that are coming out of the run at the end match what the surrogate has seen, then we can be more confident they're at least as good as the algorithm can do, if not necessarily that they are optimal overall. Equally, counterintuitive results or unexpected things like this lack of linkage, well, that might suggest to us that the model has been, well, the problem has been poorly defined, so we might need to go and revisit it. So, just to summarise, visualising the importance of variables provides some kind of basic explanations for the optimisation results. Clearly an awful lot more to go here, and that's what the current PhD project's looking at, is how can we take this further? How can we extend it to other representations, other model types? How can we automate that process rather than arranging things manually as I was doing there? I think there's probably the beginning steps of something that you might call explanations here, but it's nevertheless something that needs a lot more digging yet. So thank you very much for your time. I apologise for leaving such a small amount of time for questions. Thanks.
Thank you very much, Sandy. That's definitely a very interesting presentation. So I hope nobody minded listening to you. If you have any questions, please raise your hand. We have a question from Wei Pang from Harriet Watt. Let's make it a quick one.
Okay, very nice talk, Sandy, and
thanks, Wei.
I really enjoyed it. And I'm just wondering, have you think about hyper-heuristic? I mean, that will be more challenging, right? You're now focused on meta-heuristic. So what is your idea or option or thinking about this? Is it worthwhile? Or
good grief, I think that's probably an order of magnitude more difficult. So so hyperheuristics basically essentially heuristics to tune other heuristics, and there are some nice things that come out of there because they can learn much more general things about kind of a class of problems rather than a specific problem instance. So there is definitely something worth investigating there. I think I'm learning to walk before I run, but that's a really good thought, and I think well worth investigating.
Okay, thank you very much. Thank you.
Okay, thank you, Wei, and thank you, Sandy, for your presentation. If there are any other questions, I'm sure they'll reach out to you or the breakout sessions or through your email.
Thank you.
So this brings us to the close of the session. I'll stop the recording for now.